Hello everybody. Let us start the strengthening mechanism due to the presence of the solid solution and dispersion, hardening and at the same time precipitation hardening. So last time we have discussed the different strain hardening mechanism. Specifically in case of strain hardening, there is a increment of the strength level by the application of the further staining or further plastic deformation of the single crystal structure as well as the polycrystalline structure. Now apart from, we have discussed that several strength hardening mechanism, the effect of the crystal structure we have discussed, and the texturing, effect of the texturing also we have discussed. Now today's class we will try to focus on the mechanism of solid solution strengthening. And you know that solid solution probably in case of alloy, and in case of alloy, when there is when we add some alloying element to a pure metal, then it becomes alloy, and that actually the strength level normally increases as compared to the pure metal. But what are the mechanism behind that? So when you try to discuss the solid solution strengthening, probably we will look into that, what are the possible way the atoms can be added with a pure crystal structure. So there are two ways. Also we have discussed the defects, that is the interstitial defects and substitutional defects. So interstitial defects in the sense that when the space is occupied by the other atom and the interstitial, specifically the interstitial space is occupied of a single crystal structure, then that type of defect produces the interstitial defect, and the mechanism related to that is called the strengthening, solid solution strengthening due to the interstitial sites. Second is the substitutional solid solution. So in this case, the actual position of the atom is substituted by the another atoms, and if you see both the figures, the interstitial and solid solution arrangement of the atoms. So if you see the interstitial, the specifically smaller in size atoms takes the position of the interstitials, that we have also discussed that in crystal structure. So if we consider the unit cell, along with the atoms at all the corner points of the unit cell, there exists some interstitial sites. Of course, there is a difference in the ratio of the atoms size as well as the interstitial size, and normally the interstitial size is smaller as compared to the parent atoms in a unit cell. So if the atoms take the interstitial position, that kind of solution creates the interstitial solid solution, or substitutional solid solution, when the one atom completely substitutes the parent atom and it takes that position. So both way, normally these two way, the strengthening mechanism is done by the formation of the solid solution. Now point is that if there exists some small impurity, so specifically if we see the stress level probably different in this case. So when the interstitial site is smaller smaller impurity is there, that will try to create the stress field that is towards the sides of the interstitial. But if big impurity presents, then if you see the lattice distortion, that actually reflects in such a way that you try to create the stress field which was outward directions. So now I will try to focus on these things, the presence of the interstitial, what different type of stress generally we consider, or how we generate the stress state in specifically subjected to the presence of interstitial and substitutional atoms in case of with reference to the pure atomic arrangement of a unit cell or of a crystal lattice. Now actually the solid solution strengthening is because of the result of the elastic interaction between the stress field of the dislocations and solute atoms. So far we have discussed that due to the presence of the different dislocation, edge and screw dislocation, what type of stress field can be generated and what are the interaction of the dislocation with the another stress field of the another dislocation, that we have already discussed, and some basic idea we have provided that was related to the interaction of the stress field of the among the different types of the dislocation. So basically two types of the dislocation, edge and screw dislocations here. Now normally when you try to explain the strength hardening mechanism, so all mechanisms are directed to in such a way that how the motion of the dislocations is obstructed by the presence of the other factors. For example, presence of the any other kind of particles, presence of the any another dislocations or any other obstacles, that actually if that resistance of the dislocations motions can be created, that actually imparts in other way, it actually reflects the increment of the strength level for a specific crystal structure. So all description actually based on this phenomena, how the movement of the dislocation or dislocation of motions can be restricted. Now to do that, so here what may be the interaction between the stress field of the dislocations and the solute atoms that is responsible to analyze the mechanism of the solid solution strengthening or solid solution hardening. If we see, or we already, if you recall the fact that stress field of an edge dislocation actually having both the shear component as well as the hydrostatic components, but whereas screw dislocation is mainly subjected to shear component. That is very important statement, that edge dislocation has both an shear and hydrostatic components, whereas screw dislocation is having only shear component. Accordingly, the shear stress field surround screw dislocation is basically distortional, whereas in edge dislocation there both components are there, that is both distortional as well as the volumetric in the sense. So first figure, if you see that it is subjected to pure shear components, and second case if you see, this is the subjected to the normal stress component. So to represent that interaction of the stress field, and we have already discussed that when we analyze that there is the volumetric strain associated with actually the edge dislocations, whereas volumetric strain was 0 in case of screw dislocation. So to look into that fact, we will try to analyze the further effect of this thing, how we can bring the solid solution strengthening mechanism in this case. So if we see the solid solutions offer great resistance to dislocations motion that pure crystals, because definitely the pure crystals probably the lattice arrangement is almost perfect in absence of any kind of defect. So here we are assuming the defect in presence of only the solute atoms. So in absence of the solute atoms, the resistance to the dislocation motion is very less in case of the pure metals. But whereas in case of alloy or in case of solid solution, so it actually presence of the interstitial and substitutional atoms that actually restricts the dislocation motion. So definitely that will try to impart the some amount of the strength. Now the stress field around the solute atoms interact with the stress field around the dislocation. Based on that, actually leads to the increase in the stress required to the motion of the dislocation further. So the important factors in this case is first what are the size of the solute atoms. If the more the size difference, probably the hardening effect will be increased more. Second point is the higher the elastic modulus of the solute atoms, actually impart more amount of the strengthening effect. But overall, increased solute concentration actually leads to an increased hardening. So that amount of the or concentration of the solute atoms in the solid solution, that actually finally more impactful to decide the hardening effect on a specific solid solution. But this hardening effect actually is restricted or limited by the solute limit solubility limit of a specific solute atoms to the solution. So that is the only. So these are the overall fact related to the solid solution strengthening. Now let us see how are the important factor here actually imparts the strengthening mechanism in case of solid solution. If you observe that presence of carbon in BCC iron actually having very little solubility, say less than around 0.08 weight percentage of carbon. So therefore the approach of pure solid solution strengthening to harden a material may have a limited scope. That point is here, that since the carbon percentage is very low in case of BCC iron, or solubility limit is only 0.08%. So based on the solid solution strengthening mechanism probably having limitation to impart huge amount of the strength for the solid solution. Now what are the other factors? Size effect. The size effect depends primarily on the size. What are the difference of the size? So that is size differences in the solution, and another is the concentration of the solute. These two most important factors that finally affect the hardening mechanism in case of solid solution. So the yield strength for the solid solution is more or less or almost proportional to the more on the concentration of the solute. So rather less important here is the difference in sizes. Now for the same size difference, the smaller atom actually gives a greater strengthening effect as compared to the bigger atom. So these are the secondary point here where the size difference, but primary is basically on the concentration of the solute, and of course that is limited up to the solubility limit. So we can do the further analysis on that mechanism of solid solution. Here you can see that relative strength effect can be represented with this in interstitial and substitutional atoms. First thing is that interstitial solute atoms actually have a non-spherical distortion field. So in the sense that distortion field in presence of actually interstitial solid solutions is non-spherical in nature. So that actually non-spherical in the sense that distribution probably not very symmetric. But in substitutional atoms actually produce almost spherical distortion fields. That means approximately a symmetric kind of field can be created in the presence of the substitutional atoms. But interstitial solute atoms probably elastically interact with both the edge and screw dislocations, but whereas the substitutional atoms more only on for the screw dislocations. Therefore, the hardening effect probably in presence of the interstitial solute atoms more, because that interstitial solute atoms actually interact elastically with both edge and screw dislocation. So when it is interacting both edge and screw dislocation, so in that case it is having the effect of the both distortional effect as well as the volumetric effect also there, both. But substitutional atoms probably spherical distortion field, because in this case here it is interact mainly on the screw dislocations. So that's why, or it is subjected to the pure shear, the screw dislocation, only the distortion fields exist. So because of that, two different type of solid solution having the hardening effect, there is a difference on that. So if we look into that diagram in this figure, that solute atoms probably based on the interstitial solid solution or substitutional atoms, both types, but interstitial has a non-spherical distortion field, and if you see the relative measure of that, the relative strengthening effect with respect to the unit concentration. So in that case, if we see that in presence of the interstitial solute atoms, the strengthening effect is more, almost 3 times of the G solute. That this is just for approximate calculation. And if we see thus in presence of the substitutional solute solution, the strengthening effect is around G by 10. So in second case, since it creates the spherical distortion field, probably in this case the effect of the strengthening is less as compared to the interstitial solid solution. So further we can do the analysis. Let us look into that substitutional solid solution in copper based alloy. So in copper based alloy, if we see that the yield strength actually increases in proportional to the concentration of solutes, that we have already mentioned, that yield strength is more effective or proportional to the concentration. So in this case, but the rate of this increase is proportional to the 4/3 power of a misfit parameter. So what is misfit parameter? If you see that misfit parameter is actually the ratio of the fractional change in the lattice parameter with respect to the change of the concentration. So that can be defined as a misfit parameter here. So if you see, it's a dA by A divided by the dC. So dA by A is the fractional change in the lattice parameter and dC is the change of the concentration. So that misfit parameter actually related to that is proportional to the rate of increase. So rate of increase actually proportional to the misfit parameter. So if we see that d tau by dC, so that is change of the or increment of the stress level is as compared to the change of the concentration gradient is proportional to the misfit parameter, and here 4/3 power of the misfit parameter. So if we found out that it is proportional to this thing, and if we introduce these two constants Cg, so finally this is the expression of change of the strength level, and that if we see 1 by G d tau by dC equal to C epsilon to the power 4/3. So if we do the logarithm scale, we can find out where the C is as a constant and G is the shear modulus. So if we see that misfit parameter here, and with respect to 1 by G dou tau by dou C is actually in logarithm scale, it is actually linear. So this graphically we can represent that increment of the strength level with respect to the misfit parameter. That misfit parameter again is related to the fractional change in the lattice parameter with respect to the concentration of the solute atoms. So that relation follows the linear relation in logarithm scale. Here we see, so that scale is actually represented in the logarithm scale, and the variation is with respect to that is represents is a linear variation we observe from this figure. Now in solid solution strengthening, probably we can look into that the oversize defect, probably that the site if the occupied by the atom which is oversized, in that case the interaction energy is required to separate the dislocation from the point defect is actually positive. For sites above the slip plane, positive above the slip plane and negative below the slip plane. So in this case, that if oversized defect, if you see the stress field is basically the radially directed, and this is the overfitted atoms. So that actually try to create the stress field which shows the outward directions, and with this configuration actually it will create the with respect to the slip plane positive side and negative side, and accordingly the solute atoms will be occupied the position. So if here if you see the solute atom is occupied below the slip plane, so probably here we can consider the interaction energy in this case below the slip plane is negative. So in that position the solute atoms is actually attracted. Now if it is a oversize effect, but if it is undersize effect defect, then what will happen? If we see in the undersize defect, the interaction energy is required to separate dislocations from the point defect is negative. So if you see that interaction here, it is the undersize defect. So the stress field will be created which is towards the center point or towards the center point of the solute atoms, and with this configuration we can find out that the slip plane for the positive, the sides above the slip plane and the positive sides for the below the slip plane. So this is the positive side, and here above the slip plane actually this can be considered as a negative side. So the solute atoms will be attracted at that position, and the interaction energy can be represented accordingly, whether it is positive or negative. So these are the typical interaction for the undersize defect and oversize defect, and with this interaction probably we can decide that in case of dislocation, so at the which point the above or below the dislocation plane the atoms will be attracted or try to take that solute atoms will try to take that position. So that we have already discussed due to the mechanism of the dislocation. In that case we have analyzed the stress field due to the presence of the dislocations, whether it is the with reference to the slip plane we can define above the slip plane, below the slip plane, the positive stress field and the negative stress field, and accordingly the other solute atoms will be attracted in that position. Now if we see that solid solution strengthening mechanism, and few fact for that. First thing is that substitutional solutes is mainly attributed to interaction with stress field of the edge dislocation, that we have already pointed that substitutional solute atoms mainly the interaction with the stress field of the edge dislocation, so that it can create more the distortion at the same time there must be associated with the volumetric change. Substitutional solute atoms have little interaction with the screw dislocation. So substitutional solute atoms having very less interaction with the screw dislocation, but at low temperature many solutes in iron actually cause solid solution softening instead of the hardening. So there may be some other effect is obvious in this case, but practically if we see that there is a change of the stress level in that direction. So here if we see that there is a up to as a function of temperature, actually at the 300 Kelvin maybe room temperature, the strength level is the increment of the stress level is maximum, but below that in certain cases that it is subjected to the increment of the negative stress value. So that means at very low temperature it is actually subjected to the solid solution softening rather than hardening, but above room temperature actually the hardening effect is obvious, but increment of the stress level it actually decreases with increase the temperature. So temperature also having some effect on the solid solution strengthening effect. Now solid solution hardening by the interstitial solutes, normally we find out the carbon nitrogen, they actually try to take the interstitial positions, which is the presence of this interstitial solute atoms, the hardening mechanism is relatively higher as compared to the substitutional solid solution. But martensitic formation in steels actually considered as a separate strengthening mechanism, but martensitic is actually regarded as the supersaturated solid solution of the carbon ferrite, which is attributed to the solid solution hardening. So, formation of the martensitic structure, generally we consider the supersaturated solid solution of the carbon in ferrite, and that can be considered as that solid solution hardening. So, what are the typical mechanism actually responsible for the increment of the strength level in case of martensitic structure then? If we see that BCT structure, that is called body centered tetragonal structure, and that is generally observed in case of for martensitic. The crystal structure of martensite is generally considered as a body centered tetragonal structure. But degree of tetragonality actually increases linearly with the amount of the presence of carbon. So, when carbon percentage is 0, if C tends to 0, the lattice and the yield strength actually equivalent to the BCC ferrite. So, strength is then equivalent to the strength of the BCC ferrite when carbon percentage tends to 0. So, here if you see that percentage of carbon and corresponding the yield strength value also it is almost increases linearly, that 0 carbon percentage to 0.4 carbon percentage, there is a huge increment of the yield strength, only simply presence of the carbon, and carbon here as in terms of the interstitial solid solution in iron. Now, graphically we can see that the slope is around 575 megapascal per atomic carbon percentage. So what does it mean? It means that with the change of the carbon percentage, the increment of the with the per atomic carbon percentage changes, the increment of the yield strength is 575 megapascal. So, but if we compare practically the other cases, if we see that strengthening of copper by tin is only about 20 megapascal per atomic carbon percentage of tin. So, that means with the addition of the per atomic percentage of the tin, the increment of the strength level is only 20 megapascal, but whereas here in this case, in case of martensitic structure, here it is the slope is 575, means that is a huge, the only increment is 575 megapascal as compared to the 20 megapascal in case of strengthening of the copper alloy by tin. So, that strengthening mechanism is more impactful when there is a production of the martensitic structure, and in that case we can correlate just roughly that with the carbon percentage there is a huge amount of the increment of the strength level can be achieved. Now, this we have discussed the basic idea about the mechanism of the solid solutions and solid solution strengthening, and how we can impart the strength by forming the different solid solutions, and whereas what are the type of solid solution, interstitial and substitutional solid solution. So, increment of the strength level in these two cases are different. Probably interstitial solid solution generally produces more hardening effect as compared to the substitutional solid solution, and at the same time we have tried to interact with that presence of the substitutional solid solution or interstitial solid solution. They are interact more with the screw dislocation or edge dislocation. Accordingly, the type of distortion level can be explained when they interact with the either edge or the screw dislocations. So, let us look into the other fact, that the asymmetrical defects which is related to the solid solutions. So, many defects occupy the lower symmetry sites and hence they produce the asymmetric distortions. So, lower symmetry sites, when the symmetric level, lower symmetric sites actually when the substitutional or interstitial atoms will take into that position, that actually try to create the asymmetric distortion field. So, therefore, interact with both the hydrostatic component and the shear components of the stress field occurs when they actually create the asymmetric distortion field. So both components present there, hydrostatic and shear stress field. Therefore, when the hydrostatic and shear component stress field actually produces the asymmetric distortion, probably in that case, therefore the interaction with the both edge and screw dislocations happens, because edge and screw dislocation both actually produces the either pure shear field, and in edge dislocation actually creates the both shear field as well as the volumetric strain field. So that's why it is interact both the edge and screw dislocations. So one example is that carbon in BCC iron structure which occupies the octahedral site position. Let us see how the octahedral site position actually creates the asymmetrical defects in case of the solid solution of between carbon BCC iron and carbon. If we look into that figure, here if we see that atoms, actually E and F, both are atoms at E and F, A by 2 distance away. Actually this structure represents the carbon in BCC iron, and where asymmetrical defects results in basically higher rate of strengthening. But when we try to explain these things, if we look into the structure, these corner atoms actually represents the iron atoms, and this position actually indicates the octahedral site. So we have already discussed that in case of BCC and FCC structure, where we can find out the octahedral and tetrahedral sites also. So with reference to that figure, maybe we can look back into this figure. This is presence of the one octahedral site, how it influences the making the solid solution in case of carbon in BCC iron. So probably carbon will try to take that octahedral site position, and if you see that atoms present in E and F is basically on the same distance A by 2 A, but atoms present in A, B, C, D are A by root 2 A with respect to the interstitial site, or in presence of the octahedral sites here. Now interstitial atoms produce a tetragonal distortion. Probably if you say if it's from the tetragonal distortion, the location of the interstitial sites with respect to the atomic arrangement in case of FCC structure, this will try to create the tetragonal distortion we see. Therefore the misfit corresponding to the x and y axis remains the same, but the misfit along the z direction is different, because along the z direction their distance are different as compared to what are the distance of interstitial site with respect to the other atoms are same in corresponding to the x and y axis. Therefore interaction energy for both the edge and screw dislocations are actually comparable here, and both actually try to produce interact with the presence of these solute atoms, and there is some interaction, and there is maybe some change of the interaction energy level, but interaction energy with respect to the both edge and screw dislocations are comparable with each other. So this phenomenon actually explain the asymmetrical defects actually results in basically the higher rate of strengthening mechanism. Now another fact is that the defects with other different types of elastic constants. So a vacancy, when you look back in the crystal defects, the vacancy specifically a soft region with a zero modulus, we can consider as a zero modulus in presence of the vacancy. Now point defects can increase or decrease the modulus of the surrounding matrix. Third point is that both soft and hard defects actually induce a change in the stress field of a dislocation, and that actually leading to the inhomogeneity interaction energy. So both soft and hard defects actually influence on the stress field of a dislocation, and that actually try to bring the inhomogeneity in the interaction energy. Attractive for soft defects, which is basically analogous to the attraction of the dislocation of two free surfaces. but repulsive for the hard defects. We can find out the attractive force or repulsive force we can find out for the hard defects, but that in this case it is proportional to the 1 by r square, the size of the vacancy. Important when the misfit parameter is specifically small. If misfit parameter is very small, probably whether attractive or repulsive force or interaction energy is significant to analyze further. Now with this, the different mechanism of the solid solution strengthening, we will try to shift of the hardening mechanism for other type of hardening mechanism generally observed in the metals. So that is, you can consider the precipitation hardening. So if you see that precipitates actually may be coherent, semi-coherent or incoherent. These three types probable type of precipitates we can find out. Coherent means or semi-coherent precipitates are associated with the coherency stresses. So point is that precipitation, when you try to understand the precipitation, so there must be, we look into in terms of the coherency with the matrix structure with the base metal, what is the coherence with respect to the base metal, and accordingly we can analyze the effect of the precipitates in hardening mechanism of metals. So dislocations cannot glide through incoherent precipitates. So gliding of the dislocations mechanisms, generally it cannot happen in case of the incoherent precipitates. But inclusions behave similar to incoherent precipitates in this regard. So precipitates are the part of the system probably, while the inclusions are the external to the alloy system. So with respect to that, pin dislocations or maybe at a precipitate has to either climb over it, which becomes favorable at high temperature. So that climbing mechanism probably occurs at the very high temperature, or has to bow around the pin around it. That means in the sense the dislocations either can glide through the precipitate or dislocation can get pinned by the precipitate. So there are the two possibilities there, the interaction of the dislocations with the precipitates. And here if you see, if dislocation glide through the precipitate, if the precipitate is coherent with the matrix. So try to here you can try that further explanation of this mechanism, how the dislocation actually interacts in presence of the precipitates. So to look into that, if we see bring into that picture the dispersion strengthening, probably we can correlate into the precipitation strengthening. So here also dispersion of fine particles is actually effective in the strengthening mechanism. But what are the different ways to produce the dispersions? So one way is the precipitation of the supersaturated solid solution. This is basically happening in case of edge hardening. Second thing is that pressing and sintering of the metals powders mixed with fine particles, that actually try to produce the dispersions. Third, internal oxides, for example magnesium oxide in silver based magnesium alloy, that internal oxide actually creates the very fine particles and actually to produce the dispersions. So all these three different ways we can produce the dispersion, and that can be effective in strengthening of the structure or strengthening of the metals and alloy. But hard particles on slip plane creates barrier to dislocation. So this actually presence of the hard particles, that actually creates the obstacles to the motion of the dislocation. So by these basic mechanisms we can impart the strength level in presence of the dispersion particles. Now to continue the slip, probably to continue the slip, then two possibilities are there, either dislocation bow out or going out between the particles, or dislocations cut through the particles. Let us see these two possible way to continue the slip. What are the mechanism is responsible to create the whether bowing or it simply cuts the particles. So first we will try to look into the mechanism of that or typical conditions where the dislocation bowing between the particles. Dislocation bowing between the two particles, actually the mechanism is proposed by Orowan. We have already discussed the mechanism, but here we will try to modify little bit to fit for the analysis of the dislocation bowing in presence of the particles. Now if we look into this figure, that's dislocation energy per unit length is represented by the this amount GB square. If we assume this is the GB square and this side is the GB square, and at the semicircular form, actually this dislocation of length D actually subjected to the this force tau B into D. B is the Burgers vector here and D is the total segmented length of the dislocations and tau is the shear stress. So that actually indicates the force to that actually try to bow the dislocations surrounding the particles. Now mathematically, see, we have seen that amount of dislocation energy per unit length which is equivalently when it exactly takes the semicircular form, then we can balance this force, the tau BD, the vertical direction, and other we can corresponding to the 2 GB square. So tau can be represented 2 GB by D. So here maybe sometimes it may create some confusion that instead of GB square, sometimes we can use the half of GB square. That can also be used in certain cases, or GB square we can use it. But with this configuration, if we assume the dislocation energy per unit length equal to GB square at this point here, then we can make it balance at the semicircular form the vertical force. Then we can find out the shear stress is in terms of twice GB by D. So in terms of the shear modulus, Burgers vector, and the segmented length of the dislocations. Actually it is identical to the equation what we observed in the when we try to analyze the Frank Reed source of dislocation generation, where here we can modify the length D. Actually we can see that D is the distance between the pinning points, so basically the diameter of the semicircle. So actually the D should be here D minus dP, because the dP is the particle diameter. That means excluding the particle size, this is the effective diameter we can use, that is corresponding to D minus dP. This should be the actual size of the segmented length dislocation when with reference to the analysis what we did in case of the Frank Reed source of dislocation generation. Now the mechanism is like that. Dislocation, this is the particles, presence of the particles if we see, and this is the dislocation. It is subjected to the dislocation force or dislocation force per unit length, and that total dislocation force we can see tau B and into D. So stress field is basically the shear stress tau. So it is subjected to that kind of either stress field or dislocation stress field or the force tau BD. Then if you see that it is tried to bow around the particles, and with the further increase that things, the particle is bowing, the dislocation bowing around the particle, and actually try to leave a loop around the each particle. And if you see further bowing, this is the positive and the negative side, probably they can attract and they can produce the one loop. This figure if you see, they try to produce the loop. So that creates with the consequence deformation or during the plastic deformation and in presence of the particles, and it's a each particle this actually creates the one loop. So these loops actually prevents subsequent dislocations, and actually the loop actually effectively decreasing the value of D. So what was the initial value? Now effective value of the D actually decreases with the creation of the that such loop. Therefore, we use to predict the what is the amount of the shear stress required. In this case, it corresponds to the twice GB by D. So when D is effective values of the D actually decreases, then this actually results in the higher stress is required to form to the pass. So that actually, when there is a requirement of the higher stress, that means that that is imparting of the strength level because of the presence of this dislocation going around the particles. Now this also explains that very high initial rate of the strain hardening generally observed in edge hardenable alloy. So very initial stage the strain hardening, rate of the strain hardening is very high. Afterwards it actually decreases. Now for a given volume fraction of particles Vf, the distance D actually decreases when the particles becomes finer. That is true. For a fixed volume fraction, if you consider the distribution of the particles, if the particle size is less, effectively that actually increases the amount of the dislocation segment length between these two particles. Now consider that particles intersecting the slip plane are arranged in a square pattern. Probably we can consider this configuration. So the distance between these two particles is, we assume this is the D, and this with this configuration we can consider the square arrange. So within that two particles are there, and the distance, the edge is basically D. So with this configuration, if we see that if small r is the radius of the particle and small d is the effective distance between this particle, therefore volume fraction can be estimated like that. So definitely we are talking about the volume fraction over a unit thickness, that area occupied by the particles. If you see over this area occupied by particles, the area of one particle, that is pi r square, and the distance or the area of this square is basically d square. So here you can find out that d equal to in terms of the volume fraction, and once we find out the volume fraction, probably in that case we can use the shear stress equal to twice GB by D, and by using this equation we can further find out that shear stress equal to in terms of the volume fraction, shear modulus, Berger's vector, particle size. So here equation number 1, if we see that increase of the tensile yield strength actually caused by the precipitated particles is proportional to the again shear stress value. That means that increment of the strength level, yield strength, is proportional to the shear stress value. So if you do that, therefore increment of the stress is basically, we can represent that alpha GB Pf to the power half divided by R. So that means the increment of the yield strength actually as a function of the volume fraction, main function of the volume fraction and the particle size. So other terms are constant for a specific material or specific alloy system. Now alpha is a constant. Now if we look into that, equation 3, here if we see the strength actually increases with increasing the volume fraction, whereas that means if the volume fraction of the particles, so if the particle volume actually increases within the sample, that actually increases the strength level. That means strength hardening effect is more with the increment of the volume fraction of the particles. But at the same time, strength increases with decreasing the particle size. If particle size becomes smaller and smaller, in that case strength level can also be increased. So these are the both way it is possible to increment the imparting the strengthening mechanism in case of dispersion strengthening. That means strengthening by the presence of the particles. Therefore, in the initial stage of precipitation hardening, actually strength increases as the volume fraction of particle increases. That is true, that we have theoretically shown that strength increases as the volume fraction of particle actually increases. But after all solutes has precipitated out, the number of precipitate particles gradually decreases as the smaller ones actually dissolve and the larger ones grow. So that means the larger particles will try to grow by consuming the smaller particles. So with that effect, actually there is a decrement of the strength level. So that is typically called Ostwald ripening effect. So by this effect, the strength actually decreases. So therefore, if we see that we have observed or we have already discussed that solute particles having the either large volume fraction particles impart the strength level, but at the same time small particle size actually impart the strength level. But if we see overall this thing for a specific sample, so there is a solubility limit of the solute atoms. So therefore, when it is reached, all the solute atoms will precipitate out. At that time, probably the bigger atoms or bigger solute atoms or probably the bigger particle size will try to consume the smaller particle size. So that actually in other way the overall particle size actually increases. So in that effect, actually there is a decrement of the strength of this, decrement of the strength in the presence of the bigger particle size. Throughout the precipitation, there is another effect also, because throughout the precipitation, of course, there will be the loss of the solid solution hardening. Presence of the solid solution hardening is will be losing throughout the precipitation. So net effect of the strength level or the net effective change of the strength, probably the balance between these two effects. One is the precipitation, another is the solid solution hardening, loss of the solid solution hardening. So by compromising these two kind of mechanism, that actually defines the final increment of the strength level in case of the dispersion strengthening. How dislocation glide through the precipitate. Now we come to the second mechanism. If there is a dislocation glide through the precipitates out. So far we have discussed that dislocation bowing around the particles. Now we will try to discuss on the dislocation glide through the precipitate or through the particles. So only if the slip plane is continuous, from the matrix through the precipitate, therefore precipitate is coherent with the matrix. That we can consider coherent with the matrix. Stress to move the dislocation through the precipitate is that to move in the matrix through it, though it is usually higher as precipitates can be intermetallic compound. So coherency should be maintained here when we try to explain these mechanisms of the dislocation glide to the precipitate. Usually during the precipitation, the precipitates is coherent only when it is in small and becomes incoherent on the growth. So therefore, with this, when we try to explain this mechanism, we can neglect the growth mechanism of the precipitates. Now glide of the dislocation causes a displacement of the upper part of the precipitate with respect to the lower part P and cutting the precipitate. So in general, presence of the dislocation will try to cut the precipitate, although it is very hard. So here seeing the dislocation cut through the particles, even the particles are actually harder than the matrix. So let us see how it works. So experimentally observe that Ni3Al particles is basically a nickel based alloy have been shared by the dislocations. So if you see the mathematically, the overall strength is given by the role of mixture. So overall strength of the we can see the tau, it's a particle and the matrix the matrix strength tau mat and the particle strength is tau particle. It's like that, and we can consider the strength level based on the proportionate way what are the volume fraction of the particles. So Vf is the volume fraction of the particles here, and 1 minus Vf is the remaining matrix. So if we see that Vf is small, probably we can find out that if Vf is small, so 1 minus Vf is actually tends to 1, and the overall strength consists of the strength part from the matrix and strength part from the particle. So by combining this thing we can find out that the strength level of the matrix is this, that is represented by equation 4. So equation 4 is actually an upper limit of the value of the strength level, overall strength level. Now figure shows that this is dislocation, this is the one particles, and presence of the dislocation in such a way that actually dislocation try to cut the particles, and based on that we can find out, we can predict the strength level mathematically by following these equations and that logical reasoning on that. Now we try to explain these things. If we see that volume fraction of the second phase, that means volume fraction of the particles represent the x-axis and increment of the strength represents on the y-axis. So here we see that equation 4, that means equation 4 is represented by the, is a simple straight line. So linear relation between represent the volume fraction of the second phase particle, and we can represent these things. But equation 3, if we see that the increase of the strength is proportional to the volume fraction, and it also depends on the size of the particle. So if this is the particle size, if particle size is bigger, probably the increment of the strength level is in the lower side. But if particle size is smaller, so this, the volume fraction of the second phase actually variation, the increment level or increment of the strength actually more, since in this case the particle size is more, and that nature of the curve actually follows the equation number 3 in this case. So here you can see that the hardening effect due to the dislocations glide through the precipitate comes out due to the many factors. One of that, increase in the surface area due to particle shearing, that is the one factor that actually affect the increment of the strength level, even it is the dislocation always try to cut the particle. And the second explanation is like that part of the dislocation line segment inside the precipitate actually could face a higher stress level. So that two mechanism is actually responsible for the increment of the strength level in case of when the dislocation will try to cut the particle. But few fact on that, dispersion strengthening, the during tempering of Martensite also there we observe the carbide precipitate, and precipitation hardening effect is actually masked by the loss of solid solution strengthening for most of the steels. So it is obvious that precipitation hardening effect is actually masked, compensated, or maybe restricted by the loss of the solid solution strengthening, and it is of the for the most of the steel. So there is a two contracting effect. The one is the precipitation hardening effect due to the precipitate outs, but at the same time there is a loss of the hardness due to the solid solution strengthening effect. Therefore carbon comes out of the, because the loss of the hardness, because carbon comes out of the from the solution, so that actually try to loosen the hardness due to the mechanism of the solid solution hardening, but at the same time the carbon from the carbides that actually other way it increase the hardness level. So therefore there is some net effect can be a loss of the hardness with these two mechanism. But in case of high speed steel, tool steel, it is having the contains large amount of strong carbide forming elements. So the tungsten, molybdenum, chromium and vanadium, this actually try to impact the mechanism of the the hardening mechanism by the precipitation hardening by formation of the carbides is more as compared to the loss of the hardening due to the solid solution strengthening effect by losing the carbon atoms from the solution. So here it is more high speed still, the net hardening effect is positive, we can say the more, but in case of normal carbon steel, the net hardening effect is sometimes the loss of the hardness due to the two opposing effects of the hardening. So the hardening effect of precipitates can arise from many other sources also, or many other mechanism also is responsible for that. One of is that lattice resistance. Actually the dislocation may face an increased lattice friction stress in the precipitate, that is called the lattice resistance, that actually impart the hardening effect. Chemical strengthening, this actually arises from the additional interface created on shearing. Stacking fault strengthening, it is happening due to the difference of the stacking fault energy between the particles and the matrix, and when this both FCC and HCP, these are both present in FCC and HCP kind of structure when the dislocations are split into the partial. So stacking fault strengthening, another is the modulus hardening, coherency strengthening and the order strengthening, all are the typical mechanism actually we observe that actually impart the hardening effect of precipitates. Now this we can the way we presented this thing, the hardening effect due to the precipitate, and we have analyzed the positive this thing that mostly we in general we can find out the hardening effect due to the precipitate. So definitely try to due to the formation of the precipitate or carbide particles, specifically formation of the carbide particles impart the hardness, but at the same time there is a loss of the hardness because of the solid solution. In the solid solution there is a exit of the carbon atoms from the solid solution, and that try to form the carbides. So there is a opposing effect, or this one effect actually increase the hardness levels, another effect actually decreases the hardness effect. So the net effect actually depends on the relative amount of the this thing. With the solid solution, we can say the solid solution softening probably due to the exit of carbon atoms from the solute, or formation of the precipitates, and that is due to the precipitation hardening effect. So now in summary we can find out that typical strengthening mechanism is, first we have tried to explain the yield point. If we see the right hand side figure, so the typical stress strain diagram for specifically low carbon steel, and here if you see the stress to initiate the deformation, that is upper yield point, and stress to continue the deformation, that is corresponds to the lower yield point, and measurement of the upper yield point is generally difficult and extremely sensitive in tension test. Therefore lower yield point is the more, in most of the cases, is generally reported, since it is more reproducible. More stable point is the lower yield point. So here we are trying to summarize overall effect of the strengthening mechanisms. Probably we can look all these things in the continuum scale. Now we have seen that yield point effect probably can explain by the affinity of the interstitially dissolved atoms carbon or nitrogen for dislocations. The stress field for the edge dislocation actually attract the interstitials which lower their energy, effective energy, and but for slip to occur the applied stress must be great enough, therefore to pull some dislocations away from the interstitial atoms. So therefore when there is a lower their energy, therefore applied stress should be more enough, much enough to pull the some dislocations away from these interstitial atoms. Third point is that once dislocation breaks free from interstitials, it can move in the lower stress level. That we observe in the stress strain diagram. Once dislocation breaks free from the interstitial, actually it creates the move to the lower stress level. Therefore yielding starts at one location and spreads actually throughout the stress region. Afterwards, the strain hardening effect actually comes, and that all with this phenomena analogous to this, corresponding to the UPC microscopically or macroscopically if you see that the stress strain diagram of a specific material. So plastic deformation of single crystal occurs by the movement of the dislocations. So that we have explained that is the basic mechanism of the slip and twinning. Exception is that solid state electronic device and the single crystal turbine blade. But most of the commercial metals, commercial metal actually follows the basic mechanism of the hardening through the movement of the dislocations. But commercial metal do not deform according to the laws of the single crystal. Therefore, strength is inversely proportional to the dislocation mobility. Now, type of the slip system, Barger's vector actually determine the amount of the base stress, and then in closed pack system the stacking fault energy actually determines the extent of the dislocation dissociation. So, the purity and the method of preparation determines the initial dislocation density and the substructure. So, in the summary you can say that there is a, in case of commercial metal, probably not exactly the following the theory which is subject to the single crystal structure. So, there are several effects. So, dislocation, interaction between the dislocation and the how basic mechanism we are explaining all this hardening mechanism, that what is the stress field generated by the dislocation and interaction of the dislocations, or interaction of the stress field of the dislocation with the presence of the solute and substitutional atom. Based on that we can explain all these basic phenomena of the hardening mechanism. These are the typical fact or related to the hardening mechanism in summary. Now, strain hardening, we have discussed the Boussinger effect, Frank Reed source of dislocation generation mechanism. By this, what was the mechanism of the Frank Reed, that we have already discussed, and yield point phenomena is the mainly we have discussed on the reference to the interstitial sites presence in the structure, and how the energy level actually changes. Based on that we have explained the yield point phenomena. But in general, in continuum mechanics we represent the stress versus stress in the Orowan type of equations, or the sigma t equal to actually 2 stress is equal to some constant into strain to the power n. This is the basic law, but here n, that constant terms k and n depends on the type of materials, where n is called actually strain hardening exponent. And we have seen that in logarithm scale we can see represents the logarithm of sigma t equal to logarithm k plus n into logarithm of epsilon, that means 10. So, in the logarithm scale it is a linear, where that strain n actually represents the slope, and L and K, this represents the intercept along the axis. Now, n for the different materials, n can be like that. For HCP material, low n, BCC generally medium, and FCC is the very high values of the n. So, high n means that actually strain harden more rapidly. So, these are the just overall idea of the strain hardening mechanisms in case of the polycrystalline structure, or we can say that in continuum scale we can use this type of equations. Now, grain boundary strengthening we have discussed that the grain boundary actually acts as a barrier to deform, and the dislocation piles up at the grain boundary. So, the slip occurs at the several direction, and that essentially make a complex lattice rotations, and the presence of the grain boundaries actually impart the dislocation movement, and this actually try to increase the strength of the yield strength of the material polycrystalline structure, and that strength can be predicted by using the Hall-Page equation, where yield strength of a material sigma equal to sigma 0 plus k into d to the power minus half. That means the sigma 0 equal to base friction stresses opposing motion of the dislocations, and k is basically the locking parameter. That means extent to which the dislocations are actually piled up, and it is a function of the size of the grain size d. Then if sigma 0 is temperature sensitive, the sigma 0 can be consist of the two components. One is the temperature sensitive and the static component. We can further decompose into two components, and probably by following any kind of mechanism we can find out these two components. Also, the strength, yield strength can be represented in terms of the dislocation density, so that assume the dislocation density is proportional to the 1 by d. That means it is proportional, inversely proportional to the grain size. So these are the typical mechanism related to the grain boundary strengthening. Then we observe the solid solution strengthening specifically, and solid solution strengthening we are assuming all the mechanism, and we will try to assume that it produces the kind of the single phase structure where two or more elements combine together that actually produce more strength than pure metal. That is the basic philosophy of the solid solution strengthening. And size factor also important here. If generally the ratio between the solute and solvent less than 15%, then the strengthening mechanism is more active, and probably most interstitial impurity takes place, and that actually impact more on the strengthening mechanism by the solid in case of the solid solution strengthening. Close to the electromotive force that from the intermetallic compound, and that is not strong, not produce the strong chemical affinity. Solubility of a metal with the higher volume and the lower volume solvent, that actually impart the strengthening mechanism of that. And also the crystal structure, solute and solvent atom must have the similar kind of crystal structure. That means that it is having that is also having the effect on the solid hardening up by the solid solution strengthening mechanism. Finally, dispersion strengthening. Here we see that alloys are strengthened by the adding of the oxide particles like aluminum oxide. Actually, these oxide particles obstruct the dislocation motion, and during deformation the softer matrix actually try to flow around the particles. But at high temperature the dispersion particle does react and may or may not retain its hardness. So the hardness of the particles actually to some extent influence the strengthening mechanism by the dispersion. Finally, the precipitation strengthening, it occurs in the solid solution of the alloy. Of course, the important point is the solubility limit of the solvent is some acids, and the excess solute comes out from the solution, and that actually try to impart the strengthening mechanism in terms of the precipitation strengthening. For example, aluminum alloy, probably in between aluminum and copper, but at high temperature the precipitate alloy may disappear, and that is the case of the in heat treatment. So these are the I have tried to here the explains of the different basic mechanism of the strengthening mechanism that actually we observe, and the single crystal structure and the polycrystalline structure, and we have tried to explain all these phenomena in terms of the stress field generated by specifically the precipitation hardening and solid solution strengthening. It's to some extent it is related to the motion of the dislocations or the interaction with the stress field generated by the edge and screw dislocations, and that interaction of this edge and screw dislocation with the presence of the interstitial and substitutional solute atoms. Apart from that, we have discussed the strengthening mechanism by strain hardening, structure strengthening. Also, we have discussed the strengthening in the strengthening mechanism or effect on the mechanism for the different types of the crystal structure. So, by this explanation, all this theory, we will try to look into few problems related to all this theory. Let us look into that first numerical problem. Here, if you see that for a single crystal of an FCC metal, the work hardening rate in shear is given 0.5 gigapascal. what is the work hardening rate in tension for a polycrystal of this metal? Consider the Schmidt factor M equal to 0.32. So single crystal structure FCC metal, and we have given the work hardening rate in shear. So this is the d tau by d gamma is basically represents the work hardening rate in shear in case of single crystal structure. Now it is given 0.5 gigapascal. Now in terms of the Schmidt factor, if we observe that the relation between the stress and strain, if we see that so this is the relation actually between the normal stress and the shear stress, and in terms of the Schmidt factor actually should not be confused with the Taylor factor M, because when you try to consider the Taylor factor M for the orientation dependence, in that case we consider that this by C is actually M. So do not confuse with that. With the Schmidt factor M, this is the relation between these two. Now if we do the derivative or increment of the stress and strain, we can find out d sigma equal to 1 by m d tau. But at the same time, the relation between the shear strain and shear strain also related to this way. And here if we see, this is the shear strain, this is the normal strain, this is the shear strain. In terms of the Schmidt factor, we can correlate between this shear strain and shear strain, and if we see that increment of the normal strain in terms of the shear strain is the correlation, and if we find out d sigma by, so from equation this and from equation this, from these two we can find out the d sigma by d epsilon equal to 1 by m square d tau by d gamma. So that is the relation between the, now this actually represents the work hardening rate in tension. So work hardening rate tension, that means in tension we need to define the work hardening rate, that is the basically slope of the curve, and the slope of the curve in the stress and the strain, that actually represents the work hardening rate mathematically. Now you can find out, if we put the values of the M, we can numerically estimate what is the work hardening rate. So this is the typical problem. We can find out the work hardening rate in the shear in terms of the Schmidt factor, that in that find out the work hardening rate in case of tension. Because work hardening rate in case of shear we can easily find out for single crystal structure, but work hardening rate of the polycrystalline structure, using that value and using the simple Schmidt factor, we can find out the work hardening rate in case of the polycrystalline structure. So this is one typical example. Now if we can look into that another example, that consider dislocation blocked in a copper crystal if the flow stress is controlled by the stress necessary to operate Frank reed source. Compute the dislocation density rho in this crystal when it is deformed to a point where the resolved shear stress in the slip plane is 42 megapascal. So here we need to consider the shear modulus G equal to 50 megapascal. Now here it is mentioned that stress necessary to operate Frank reed source. So according to the, when we consider the mechanism of the Frank reed source of dislocation generation and at the semicircular form, we can directly estimate the shear stress to make the dislocation bows to the semicircular form. The relation between the shear stress and the shear modulus, Berger's vector, and d equal to actually distance between the 2 point of the dislocation. So sorry, this is the d distance between these 2 point. Here if we see that we can estimate easily the shear stress required in this case, or maybe shear, I think shear stress is given. So N twice G, I think for the copper we can easily estimate the B, and now from here we can find out what should be the distance D. Distance D means the segment of the dislocation. D we can estimate by looking into all the on that slip plane the resolved shear stress and resolved shear stress, shear modulus, and the Burger's vector we need to calculate in case of the copper. By available data we can easily find out what is the Burger's vector in this case, and there we can find out what is the D. So once we estimate the D, so from there we can find out, by estimating the D we can find out the dislocation density by looking into the relation between the D and the dislocation density. Now if we look into the problem 3, here we need to calculate the stored energy in a copper crystal with a dislocation density of 10 to the power 11 centimeter square. So dislocation density is given here. Now here we need to find out stored energy. So we know that stored energy approximately calculated by dislocation energy per unit length is approximately 1/2 of g b square. So once if we estimate the B for copper, you can easily estimate the Burger's vector B, and from there we can find out the dislocation energy per unit length. So here we can find out now, so 1/2 GB square actually dislocation energy per unit length. Now if we multiply by the dislocation density, so here we can find out what is the energy associated for a specific sample. That means if one sample over the volume, if the dislocation density is estimated, that means dislocation density is given here. So for that sample we can find out the amount of the dislocation energy associated with the total number of dislocation with the sample. But this is the one way we can estimate that directly straightforward. What is the amount of the energy associated with this. Now there is another way to estimate these things, but you need to know completely the stress strain behavior in the second case. If we assume the stress strain behavior of copper crystal follow this thing, and of course considering the strain hardening or work hardening effect, sigma equal to sigma 0 and k epsilon to the power n. This is the typical stress strain diagram in case of the copper crystal. So we need, if we completely define the stress strain, and at a specific point, suppose this is the point, at this point if we know that strain equal to E1, for example, amount of the strain E1, and at this point the strain equal to sigma, so that here at this specific point sigma, the stress we reach at that point from the base stress sigma 0, and remaining part by the work hardening mechanism, through the work hardening mechanism the strength actually increases up to that point. So at that point sigma is given. So once the stress strength curve is defined for the specific material, or for the in this specific case, in that case the energy per unit volume can be estimated like this: 0 to epsilon sigma d sigma. So from here we can find out that the amount of the energy is, if we put it sigma equal to in terms of sigma 0 and integration limit from 0 to epsilon 1 and k epsilon to the power n d epsilon. So here we can estimate that energy per unit volume in this case from the strain hardening mechanism. So if the sample volume size is defined, multiply by the total volume, so total amount of the energy associated with this can be estimated. Now we can compare this thing, that which cases the amount of the energy is more or less, or both way we can estimate the total amount of energy, stored energy in a copper crystal with the dislocation of density. Specifically with this amount of the dislocation density is a heavily deformed material. So highly deformed material, this amount of dislocation density generally exists. So these are the way we can estimate the amount of the energy associated with the specific sample. Now if you look into the problem 4, here we see, consider a material strengthened by precipitation of fine particles. Suppose shear yield strength of the particle is G by 10. That is the theoretical strength that we discussed, that theoretical strength is G by 10. So G is the shear modulus and the strength of the matrix is G by 500. So these are the two strength level are given. Also assume that the volume fraction of the particles is only 1%. That means volume fraction of the particles is 1%. That means VF means 1 by 100. And have a diameter of 0.01 micrometer. So D, the particle diameter is equal to 0.01 micrometer. Assume that B equal to 0.2 nanometer. That means Burger's vector is given 0.2 nanometer. Need to estimate the applied shear stress which is necessary to bow the dislocations between particles. So what may be the applied shear stress so that it bow the dislocation between particles, and would dislocation bow between the particles or it will try to shear them. So first we look into that first questions, that what may be the applied shear stress that will try to bow the dislocation between the particles. So in this case we assume the situation is like that. During the bowing the dislocation will try to form the semicircular form. So when you try to form the semicircular form, in that case the shear stress is required, shear stress is equal to twice GB by T. So here if we see the G shear modulus is defined, B Burger's vector also defined, but we need to find out the D. So D can be found out because the volume fraction is given here, and if we assume the volume fraction of VF and probably over a sample with this configuration of a square element, with the configuration of the particles of a square element. So here if we assume that the distance between these two equal to D, so in that case volume fraction can be represented by pi r square by D square. So pi r square is the surface area or per unit thickness surface area of the particle, and D square is the surface area of the square. So this ratio indicates the volume fraction. So volume fraction is given and particle size also given. So from here we can find out the length, dislocation length between the length of the segmented length of the dislocation or distance D between the two particles. So once we estimate the D, and if we put the D value here, then we can find out the shear stress value requirement. Now this shear stress value again we can find out also the other way. If we assuming the particle is caught by the dislocation, so in that case the shear stress required to cut the particles is the mixture of linear mixture of these two components, or is the volume fraction of the matrix, volume fraction of the particles. So both the strength of the matrix and strength of the particle also given, and volume fraction also given. So from there we can find out what may be the shear stress value. So now this shear stress value and this both the shear stress value we can compare. Now if the shear stress, this which cases if the shear stress value is actually cross the shear stress to cut the particle, then we can say that the dislocation, so therefore the dislocation bow between the particles or shear them, accordingly we can take the decision by comparing the shear stress value on the first case and in the second case. So let us look into the another problem related to the strengthening mechanism, that a high strength low alloy steel is strengthened by precipitates of particles. If the diameter of the particles is 50 nanometer, what volume fraction particles would be required to increase the strength by 100 megapascal? Atomic diameter is given. So if we see the high strength low alloy steel is strengthened by precipitates of particles. So diameter of the particles is given. So diameter D of the particles is given 50 nanometer. What volume fraction would be required to increase the strength by 100? So the increment of the strength is requirement. So delta sigma equal to 100 megapascal here. Now we need to find out from here what should be the volume fraction requirement. So if this equation, if you see the particle size is given r, or particle radius of the particle is given, shear modulus, you know the high strength shear modulus, it's generally known alpha probably in this case we can use alpha equal to 4, and B Barger's vector, I think here B is equal to the 50 nanometer. So B Barger's vector, in this case we can consider the atomic diameter. So atomic diameter means probably we assume the close back direction. So in this case full Barger's vector can be represented the shortest repeat distance, which is equivalent to the atomic diameter in this case. So B is the Barger's vector, is basically atomic diameter here. Now we need to find out, once G is given, we need to find out VF from this equation. So probably with the several problems related to the strengthening mechanism, actually this will try to make the more clear understanding of the strengthening mechanism. Specifically is generally we apply either in single crystal structure or polycrystalline structure, or in general in case of metals. Thank you very much for your kind attention.